characteristic impedance of the transmission line normally, but it'd be the characteristic impedance of the waveguide. That's going to be times ZL plus JZ0, tangent of beta L, and this is beta in the guide L, over Z0 plus JZL, tangent of beta in the guide times L. So that would be Zn for a waveguide. You all know what I'm talking about here? I'll give you that equation. You have to understand what beta G is beta in the guide. It's not just omega times square root of mu epsilon. You all follow me on that, guys? L is the wave. I'll give you that one. I'll send you a formula sheet. I don't remember of other formulas you need, but you can bring a rotated Smith chart. And in other words, the one with the rotated Smith chart thing, you can print out several. I'd bring them to bring a good sharp pencil, and because you will get something with L section matching. So I'm just telling you, you're going to get that. I was going through this just before I came down to things I would suggest reviewing. So I get a question like this, and everybody asks it a little differently, but they're after the same information. For the final exam, it's the best way to study. So I tell people this: go through the quizzes first. Make sure you understand how to do each and every quiz, both A and B. Right now, all the solutions are posted. Make sure you know how to do the quizzes without any concern. If you have concerns, then put your attention there. The second thing I say is go through the homework, starting at the earliest homeworks. Now, a lot of the problems are just the same class of problem. There's different variables and stuff like this, but make sure in the sections you know how to do all the problems. And if you don't, then focus on the problems you don't know how to do. And make sure you can come out. I would start the earliest part, because the information you just had is most current. You're more likely to forget the stuff in the beginning. People ask me EMAG 1 stuff. It says technically we're supposed to quiz you on EMAG 1. I'm not going to ask you how to calculate capacitance, inductance, and stuff like this. However, you know, for the resistance of a wire, there's AC and DC resistance, right? To me, that checks a box. That's EMAG 1, calculating the resistance of a wire. Everybody follow me on that? You're going to have to know something about, remember, we spent some time doing the actual spectrum, frequency spectrum, for a standard rise time, on time, fall time, with a certain duty cycle wave. And the EMC stuff that we did related to that, you're going to have to understand and know how to do. You all follow me on that? This stuff was not in his book, but I posted a lot. Everybody follow me? All right, I'm going to give you a question on that. There will be a waveguide question. There are going to be antennas questions. There's going to be a radar question. There's going to be an L section matching question. And these are multi-part. There will be something with S parameters. And there's going to be something from chapter 6, which has to do with wave propagation. And I can work in shielding and wave propagation in one problem. So there's 6 to 7 problems. I haven't made it out yet, so don't ask me how many problems are on there. I haven't made it out. I think it's going to be 6 to 7 multi-parts. It's really not 2.5 hours long. I say normally it's about an hour and a half for a person who knows what he's doing. You can get through that without any problems. However, it is closed book. Remember that. And all the formulas that you're going to get, I'll provide you. But just working problems, you should be familiar enough with them. All right? Y'all follow me on that? Now, the stuff that we're doing here, the quiz, on the filter, I'm not going to ask that at the final. Y'all hear me? I'm not going to ask that. That was something I don't normally cover, but based on my conversations with some other people, that you should at least be aware of Chebyshev filters and some of the filtering aspects of that. We didn't cover Butterworth. So, now, anybody have any questions about material throughout the course, not just relative to the quiz now? Because yeah.
I guess this isn't just about material, but are there any other topics other than the filter content that will be on the final?
I like this. Eliminate what I don't need to study. Well, I'm not going to ask you anything about fiber optics, but I think I made that clear several times. But other than that, it's fair game.
The waveguide.
Yeah, the waveguides.
Traditional waveguide.
That's right. It's gonna be rectangular waveguides and, the stuff that we've done already. In other words, if you don't remember, there was one mode that was very important. It was the TE10, right? And that was the one that probably I'd understand how to do. And I'd understand over what band it works. Like from there to double that cutoff frequency of the 1 mode, that's the range where you're gonna operate a typical waveguide. I'm not gonna try to fool you on any of this stuff. It's gonna be standard stuff, and if you look at the quizzes, they're very representative of the final. How many have had me before? All right, if you had me before the final exam, did it reflect all the quizzes? And there's nothing new that's gonna come at you, other than the fact that now you're gonna be expected to remember stuff from the beginning of the course, and that sometimes can push you, especially when you have to do wave equations, stuff like this. I will not ask you to recreate the wave equation, but you will be expected to know the solutions so that you can figure out parameters like alpha and beta. How about this? Just let me ask you this. For a good conductor, what's alpha and beta?
Equal.
They're equal, right? That's one way you can tell right away. They're equal. All right, what is the intrinsic impedance for a very conductive media, a very good conductor? Tell me one thing about it. It's got an angle of 45 degrees. Do y'all remember that? Guaranteed. And there are certain things that just knowing that you can spot the actual solution to a problem fairly quickly. Right? I'm trying to think of things I would want to know if I was sitting with you. I just tell you, when is our final again?
Tuesday.
At what time? Tuesday at 12? Oh gosh. All right, my one thing I recommend, and this is based on a whole lot of stuff I've seen over the years, including my own personal experience, get your sleep. The one single thing you can do to benefit your performance is sleep. Lack of sleep is the single biggest problem to memory and just rational thought. And I've got stories and stories about people that take stimulants. I had one kid came into my class, and he told me about the virtues of Adderall. This is a long time. It's hilarious. And this kid said, I aced your test. I studied last night. I got everything. And he absolutely believed he just knocked out. Everything was wrong. But he was absolutely convinced everything was right. I've never seen anybody like that. I'd start showing him, he'd be in shock. So I'd warn about not getting sleep, because that's the single thing that'll probably hurt you more than anything. I'm not kidding about that either. Anyway, I'll not say too much more about that. You can don't bring anything that goes crunch or anything that's going to cause a problem, but you can bring in, if you want Coke or tea or coffee, I'm not going to say no, you can bring it in, but please, just nothing that makes a mess or disturbs people. All right. Okay, no other questions? I almost feel we should do something from the earlier part of the course, because we have it from at least chapter 5, and maybe we can work in a problem of shielding the whole 9 yards in chapter 5. How about we do this? Because I want to do one of them. So this would be a kind of final exam problem. I give you something made of copper right here, and copper has a conductivity of 5.8 times 10 to the 7th, 1/ohm meters, and it's got an epsilon relative equal to 1 and a mu relative equal to 1. So this is a copper shield, and it's got a thickness, a certain thickness. And I've got an incident wave coming into it. And I want to know the transmitted field. So I want to know the transmitted field. And then I'm going to get the actual shielding effectiveness. Y'all remember this kind of problem? Now I can make that thickness anything I want, but we're going to assume something. We're going to assume that the thickness is much greater than the skin depth. So a skin depth is what? Y'all remember this? Square root of pi f mu sigma, right? Y'all remember? I'm going to remember that at least, all right? You're going to have to know skin depth. That's the skin depth. It's 1/square root of pi f mu sigma. Now the next thing we need to know, we're going to assume this is air. And assume this is air. That's typical. And we're going to assume that means eta naught is what? 120 pi ohms. Here it's going to be eta 120 pi ohms. But now we need eta of the shield, right? So what is eta of the shield? Anybody remember? Square root of what? J omega mu, typically it's sigma plus J omega epsilon. Y'all agree with that? And it doesn't really matter what the frequency is at this point. And omega is equal to 2 pi f. Now, if it is a good conductor, and copper is a pretty good conductor, so we're going to assume sigma is much greater than omega epsilon. If it isn't, you're at a frequency that's so high, we can't even do this problem with a standard electromagnetic approach. It's optics. All right, that means this is approximately what? It's approximately square root of J omega mu over sigma, or it's really what? Square root of omega mu over sigma e to the j pi over 4 or 45 degree ohm, right? Y'all remember this class? All right, now after that, remember I'm after the transmitted field, so what else do I need in this problem? This is something we haven't talked about in a while, but I think most of you realize it. What's the next thing I need? How about reflection and transmission coefficients, right? All right, let's get the transmission coefficient right here. So the transmission coefficient right there between air and that media, and we're assuming that it's very thick. It's not just half a skin depth. It's much thicker. It's call it 4 or 5 skin depths thick. So we don't have to worry about multiple reflections there. So if we get this, tau 1 is really what? 2 times eta of the shield over eta of the shield, right? Plus eta naught. Y'all remember that? Now, if we assume this, that the magnitude of eta shield right here is much, much less than eta naught, you can say this is approximately equal to what? 2 times eta of the shield over just eta naught. And the reason you can do that is because this eta shield is much, much less than eta naught. Y'all follow me? Everyone? Back there? All right. Now, if that's the case, I got the transmission coefficient right there, right? What about the transmission coefficient here? Well, it's always twice the impedance you're going into. Y'all, you remember this, guys? It's always twice, you could say it's 1 plus the reflection coefficient, but the way I like to do it, it's twice the impedance you're going into, so it's 2 times eta naught over what? Eta naught plus eta shield, right? Now what is that approximately? Take a look. What about these two? Eta shield is much less than eta. This is about 2. Y'all follow me on this, guys? You remember doing a problem like this? I hope you do. So this is about 2. Okay. Now when we take a look at E transmitted, just in magnitude, forget the phase on this one. What is it going to be? Well, you take E incident, right? E naught incident. Then I multiply it by what? Tau 1, correct? That's the transmission coefficient. And we'll just take the magnitude of that. So that's the amount that gets in here. That's the amount of this field that actually is in here. Now, the field that gets in here is going to what? Asymptotically decay versus distance. Y'all follow me? Normally it's e to the minus alpha times the thickness, right? That would be the magnitude of the decay, and we can forget about phase. And alpha is 1 over the skin depth, so you could write it like this. It would be e to the minus, and it could be the thickness over the skin depth, because remember, alpha is equal to 1 over the skin depth in a good conductor. You remember that, everyone? How many do? All right. If you don't understand that, you can just write the equation. Remember, gamma is equal to alpha plus j beta, and in a good conductor, this is square root of j omega mu. Here it's sigma plus j omega epsilon, but if it's a good conductor, you forget that. And that's just equal to square root of j is 1 plus j over the square root of 2, and that's times square root of omega mu sigma. And that's exactly equal to 1 plus j times square root of pi f mu sigma, which is 1 over the skin depth. That's the reason I'm pointing that out. Alpha and beta are the same in a good conductor, and they're equal to 1 over the skin depth. Y'all follow me on this, guys? You can all see it back there, too. All right. So we have this. This is just the skin depth. Then we have to multiply by the transmission coefficient here, which is just 2. And that would be the magnitude of the transmitted field. Do you all agree with that? Now what is shielding effectiveness? It's in dB for starters, right? Shielding effectiveness, it's 20, right, times the log. And remember, this is gonna be a positive number, so you could take it as E naught incident over E naught transmitted, or you can make it minus 20 times the log of E transmitted over E naught incident. It's gonna be a positive number. That's gonna be equal to 20 times the log of, and then you can go ahead and say, it's really gonna be 1 over, and it's gonna be tau, magnitude of tau 1, times 2, because tau 2 is equal to 2, times E to the minus T over the skin depth, and that would be the shielding effectiveness. Do y'all follow me? Now we've neglected the multiple reflections. There's going to be reflection from here to here, from here to here, and from here to here, and so forth. But if this thing's dying down, if it's much greater than skin depth, which most shields are, almost all, then by the time it reflects here and gets back, it's virtually non-existent. It's so far into the noise. But that's a typical shielding effectiveness problem. And I could ask you something like this. What I might do is ask this. I might say, if this, I think I did on the quiz, I give you the transmitted field, I ask you for the incident field, right? Or was the other thing I asked about? Magnetic field, right? Here's you've got to be careful. Remember, the transmission coefficients and reflection coefficients are based on E fields, not H fields. So, if I asked you for the magnetic field in here, if I wanted you to get H inside this region, H in the shield, how would you get it? Well, you would get E in the shield, right? First. And then if you had E in the shield, you divide it by eta of the shield to get the H field. So if I gave you an H field out here, you wouldn't just take that H field and multiply that by the transmission coefficient to get the H field in the shield, all right? You work with E fields, then use eta to get the H field. Do you follow me on this class? One other thing, if I asked you for the power density out here, how would you get it of the transmitted field? Power density. It's still in air, right? How do you get it? Propagating wave in air. 1/2 magnitude of the E field squared over eta naught, right? That'd be in watts per meter squared. But how do you get the power density in the shield? That's a good conductor. Remember the one thing about that? What did you have to do? I'll put it right here. In general, average power density is what? It's 1/2, right, times magnitude of eta, in this case of the shield, right? It's the magnitude of E in the shield, I'll just call it E in the shield, right? Squared, but then it's what? It would be technically times E to the minus 2 alpha Z if it was propagating in there. But there's also the cosine of eta, of the angle of eta of the shield. Do you all remember that cosine effect class? How many do? Couple of you? All right, remember that's in a good conductor, and that angle is 45 degrees, so it's the cosine of 45 degrees, which is 1 over square root of 2. Okay? I'm just trying to show you some of the stuff that you can stumble on. Now, typically when I do a problem like this, almost all problems, I'll either give you the E field, H field here, or I'll give you the E field, H field here, and I'll ask you for the other components, power density, things like that at different points. That's basically how I do these problems. Y'all with me? I'm not going to ask you anything about oblique incident wave. Y'all remember that? It's only going to be normally incident, but you have to remember how to get the actual reflection coefficient and the transmission coefficient for normally incident waves. Those are the things we haven't talked about. One other thing we haven't talked about in a while is antenna gain and directivity. You all remember that? All right, please review that. The reason I'm saying this is, remember, for antenna gain, I just mention this before I move on. By the way, the senior projects, I guess the capstone projects that we showed today, between 2 and 4, I think. That's what message I got. Is anybody, well, you guys aren't graduating, but I don't think anybody here is in those things. But it's always neat to walk around and see what they've done, to get an idea what you can do. All right, when we talk about antenna directivity, this would be EMAG. Remember how we did it? It's what? 4 pi over. Right, 4 pi, and it's over what? Yeah, it would be really 0 to pi, 0 to 2 pi, and that's the normalized power, radiated power, then it's times the sine of theta times, in this case I put d phi first, then d theta on the outside. But you have to remember, this is called what? That's the solid angle, remember that? Right. Now, that's something you haven't done in a while, so it would be smart to review that. And to get that normalized power, remember the one thing about it is you find the maximum value of the normalized power, holding R constant, and then divide the actual power density for any angle by that, so that the peak value of that is 1, and it can never be more than 1. These intervals, by the way, for the most part, these are just trig substitutions, like if it's a sine cubed, it becomes cosine squared times sine theta, and the cosine squared right there, make u cosine theta du minus sine theta d theta. But you also, these days, you have calculators that do symbolic integration, I think. You don't? How many have calculators that do that? I thought a lot of them did. What?
I use an older calculator.
Well, pardon? I mean, really, it doesn't matter if you do them or not, because these are standard integrations, and the only one I really worry about is the sine cube integration, because that's the one that pops up all the time, typically. All right. I'm trying to think of anything else I could go over, but I think you pretty much know what's coming at you. Overall, the class is doing pretty well, and I'm happy. So now I'm going to give you a quiz, unless you got anything else. Anything? Some of you look pretty tired. Did you have a test today or something? Yeah. Final exams in this room at 12 o'clock Tuesday. And if anybody needs to know when your final exams are, Auburn has a website. Just Google Auburn University final exam schedule fall 2022. You can find it. I enjoyed this course. All right, this is open book, so you can leave your books open, but it's closed notes.